increasing and decreasing functions, and also the first derivative test. We want to be able to determine the intervals for which a function is increasing or decreasing, and then apply the first derivative test to determine the relative extrema for a function. Those are our two objectives. First, the definition for increasing and decreasing functions. A function f is increasing on an interval when for two numbers x sub 1 and x sub 2, where we have that x sub 1 is less than x sub 2, implies that the function values f of x sub 1 is less than f of x sub 2. The function values are getting larger. For the function f that's decreasing, for x and for any 2 points x sub 1, x sub 2, such that x sub 1, x sub 2 is x sub 1 is less than x sub 2, we have f of x sub 1 is greater than f of x sub 2. The function values or the y values are getting smaller. So when you talk about increasing functions and decreasing functions, it's easy to extract the first derivative. When the first derivative is negative, that simply means that the function is decreasing. When f prime, the derivative is 0, we have a horizontal slope or constant function. And when f prime of x is positive, then the function f is said to be increasing. So this is a neat way to determine increasing and decreasing intervals. The test for increasing or decreasing functions, or by which the function is increasing or decreasing, check the first derivative. First, we find the critical point, and then from the critical points, we partition the number line, and then you pick values within that number line to test within f prime of x. If f prime of x is positive, then for that particular interval from a to b, the function is said to be increasing. If f prime of x is negative on the interval from a to b, then f is said to be decreasing on the closed interval. If f prime is 0, then the function is constant on that particular interval. The first derivative test, I think once you take the number line, you partition the number line based on the critical values, and you determine the intervals by which the function is increasing or decreasing. There you check those signs. If f prime changes from negative going down to positive, that means you have a relative minimum at the point c comma f of c. If f prime, second situation, if f prime changes from positive to negative, then you have a relative maximum. If f prime of x is positive on both sides, or if it's negative on both sides of c, then there is no relative extrema. There is no maximum minimum there. The function is said to be constant for that particular interval. That's number c. So here are the examples where here f prime for the first part is negative on the left side of c, then it jumps to being positive, so you have a relative minimum. For the second example, f prime is positive here on the left side of c, and then on the right side of c, f prime is negative, so you have a relative maximum. Here at c, the function is increasing on the left side, and then it also increases on the right side. So here we do not have an extrema. Something else happens there, and we'll talk about that in the next section. And the same thing here. For these two graphs, we have no extrema. Now here are some steps that I think are useful to determining the relative extrema. Determine the critical points by finding the first derivative and then setting the first derivative equal to 0. Partition the number line based on these critical values and the points by which the function is said to be discontinuous. From there, part 3, determine the increasing and decreasing intervals by checking the signs of f prime based on those intervals that you have determined from step number 2. Apply the first derivative test and then find the extrema if they exist. You may want to find other helpful graphing aids such as x and y intercepts. Graph and label all the points that you found above. Let's see. Let's take this problem. We find the critical values, find the intervals of which the function is increasing and decreasing, and then apply the first derivative test graph after that. So we find first f prime of x. This is 6x squared plus 6x minus 12. Now we set this guy equal to 0. So this implies that we have, if you factor out an x, a 6 that is, we have x squared plus x minus 2. I think we can factor again x plus 2 times x minus 1 is equal to 0. If that be the case, this implies that x is equal to negative 2 and x equal to 1. These are our critical points. Now the next step we do is partition the number line based on these critical values and to consider f prime, right? So f prime of x is equal to 6 times x plus 2 times x minus 1. So based on the critical values, the intervals are going from negative infinity to negative 2, just counting from less than to greater, and then from negative 2 to 1, and then from 1 to positive infinity. Here we test f prime. We test its sign. So from negative infinity to negative 2, f prime, let's take any number on the interval. Let's take negative 5. Plug in negative 5 here and negative 5 there. We get negative times the negative. We get positive. Take a number on the interval from negative 2 to 1. Let's say 0. Plug in x equals 0. We get negative. Take a number on the interval from 1 to infinity. Plug it in for x. Take the number 5. The other one was negative 5. If I didn't see it, I meant negative 5 over here. So let's take positive 5. Doesn't matter. Any number on the interval from 1 to infinity. Plug in the 5 there and 5 there. We get positive. So the plus sign means increasing. Here is decreasing. And here increasing. Now, so at negative 2, it goes up and then it goes down. So that means that we have here a relative max, a relative maximum at negative 2 comma f of negative 2. F of negative 2 is equal to 2 times negative 2 to the third plus 3 times negative 2 to the second minus 12 times negative 2. And that gives us 20. Now at 1, look at 1, it goes down, then it goes up. So we have a relative minimum at 1 comma, this is 2 plus 3 minus 12. So we get negative 7. Now, what might be helpful is to get an intercept. Here, when x is 0, we get 0 for y. So 0 comma y is it's x and y intercept, so we just say it's an intercept. We get another one, but if it's too difficult to get an intercept, then I'll try to avoid it at all costs. Now let's see what we have. Let's see, maybe graph in red. All right, so we know it touches down at the origin. We have a maximum at negative 2, 20. Then we have a minimum at 1, negative 7. So this point here was our minimum, and that was at 1 comma negative 7. Our intercept, and this was the point negative 2 comma 20, and we had a relative max, relative minimum. Okay. Well, let's keep digging. Look at the next problem. Find the derivative f prime of x. It's the derivative of the first, which is 2 times x minus 1 times the second, plus the first times the derivative of the second. And the derivative of the second is just 1. So f prime of x, factor out x minus 1 to help me in the simplification. So I've left 2 times the expression x plus 3. So that's 2x plus 6 plus x minus 1. And so we get x minus 1, yes, times 3x plus 5. We set the derivative equal to 0. This implies that x equal to 1 and x equal to negative 5 over 3. So now we partition the number line based on this information. So we go from negative infinity to negative 5/3, and then negative 5/3 to 1, and then from 1 to positive infinity. And we investigate the signs here of the first derivative. So let's take a number on the interval from negative infinity to negative 5 over 3. We're going to plug that into our first derivative, and I'm looking at this guy right here. So just take negative 5. This is negative, and that's negative, so we get positive. Let's take 0 on this interval, plug in the 0 there, we get negative. Positive, so we get negative. Take a number positive bigger than 1, say 5, positive, positive. So at negative 5 over 3, the graph goes up and then down. So here we have a relative max at negative 5/3. Plug in f to equal to negative 5/3, and that gives us 256 over 27. And then at 1, it goes down and then up. So we have a relative minimum at 1. Plug in x equal 1, we get 0. That's easy to get. Well, let's see. What happens when the function is 0? So when f of x equals to 0, this implies that x minus 1 squared times x plus 3 equal to 0. That gives us x equal to 1, x equal to negative 3. So in other words, we have 1 comma 0 and negative 3 comma 0 are our x-intercepts. Now when x is 0, if x is 0, then I get negative 1 squared, which is 1 times 3 is 3. This becomes our y-intercept. So now we graph. I think I can get everything on this. Let's see. We'll try. So we have the y-intercept. X is negative 5/3. Y is up here for our maximum. We have a minimum. X is 1 and y is 0. And then we have x-intercepts at negative 3 comma 0. So I'm just going to go ahead and just graph. And the y-intercept is crossing like that. Hope this color comes out. So this is the minimum, 1 comma 0. This point was our relative maximum. Guess it just doesn't like my A. That's the point negative 5/3 comma 256 over 27. And then this point here was negative 3 comma 0. X-intercept, and then also you recall that this point here is also an x-intercept as well. It has dual characteristic. It's a relative minimum and the x-intercept. That color there looked pretty cool, so let me try that. Yeah. I'm not too satisfied about how that 3 came out. So it's negative. Okay. We found the first derivative. So we get 2/3 times x plus 2 to the 2/3 minus 1, or 2/3 minus 3 over 3. So it gives us negative 1/3, then times the derivative of the inside, which is just 1. So what we have here is 2 all over 3 times the cube root of x plus 2. The cube root, right? Well, notice here that f prime does not equal to 0. But we have a point of discontinuity at x equal -2. So at x equal to -2, f is discontinuous. So we partition based on this point of discontinuity, which is also a critical point. The critical point was defined in 2 ways. One, either you can find where the derivative is equal to 0, solve for x, or the point x is a point of discontinuity for the first derivative. So here we have the interval from -infinity to -2, excuse me. And then from -2 to +infinity. Here we examine f prime. So take a point from -infinity to -2. Let's take -5. Here this is being plugged into the first derivative. We get negative. This is the cube root, not square root, not square root. So we get negative. We get positive there, right? So this means that we have a relative, it goes down and then up. We have a relative minimum at here, -2. Let's see, f of -2 is equal to 0. So relative minimum at the point -2, 0. Well, I think from here, I think we're ready to just go ahead and graph. You can find those points of intercepts, if you will, if you plug in. Well, this -2, 0 is already our x-intercept. If you set x equal to 0, x is 0, we get y to be the cube root of 4, right? 2 squared, and it's the cube root of that. So the point -2, 0, let's see, is there. And in terms of the graph, I just have to just draw it fast, because when I take time and try to draw everything like it's supposed to be, I always mess it up. So it's a parabola. It's not a V. It's the thing about labeling the point first. Okay, and this, okay, that's fine. This point is also the x-intercept. All right, let's look at this one. This problem, we could work using just algebra alone and get it. But we'll use calculus. That's why we're here. So f prime of x is equal to the derivative of the numerator, which is 2x, times our denominator, x squared minus 9, minus our numerator, times the derivative of our denominator, which is 2x, divided by the denominator to be squared. We simplify that, we get 2x to the third minus 2x to the third cancels out. And then this is also a negative 18x in the numerator, so negative 18x over x squared minus 9 to be squared. Now if you set f prime equal to 0, this implies that negative 18x over x squared minus 9 to be squared is equal to 0, which implies that x is equal to 0. And we also have two other points that are critical points, and that is when x is equal to plus or minus 3, because it's discontinuous in our denominator at plus or minus 3. So x equal to 3, x equal to negative 3 are our critical points. So we now partition the number line based on these critical points. This is negative infinity. We go from least to the greatest. Negative 3 to 0, 0 to 3, and then 3 to positive infinity. We check the signs of our derivative. This derivative is being plugged into the first, the number is being plugged into the first derivative. Let's take a number from negative infinity to negative 3. It's a negative number. Negative times negative is positive. Our denominator is always positive. So we get plus. Take negative 2, plug it in here. We get negative times negative. That gives us positive. Take the number 1. Negative 18 times 1 is negative. The number bigger than 3, plug it there, we still get negative. All right. So the only extrema that we have is at 0. See, the sign changes at 0. It goes from plus, is going up, and then at the right side of 0, it goes down, negative. So we have here, and you plug in x equals 0, we get y equals 0. So we have a relative maximum at 0, 0. Okay. And that, by the way, if you check it, is our only intercept as well. Now, if you recall from algebra, that this is what we call a rational function. And with the rational function, you could find some graphing aids here, horizontal isotope, vertical isotope. The vertical isotope would be at the plus or minus 3, where we had discontinuity there. So our horizontal isotope, usually I just say HA, is the line y equal to, well, if you remember, you look at the power of your numerator and the power of your denominator. If they are the same, then the horizontal isotope, which is the limit as well, is the ratio of the leading coefficients. Well, our powers are the same, so the leading coefficient is 1 divided by 1. We get 1. If the power in our denominator was greater than the power in our numerator, the horizontal isotope or the limit is 0. And if the power in the numerator is greater than the power in our denominator, then the horizontal isotope or the limit would be infinity. Okay. Now, what about the vertical isotope? Here, look at your denominator, set it equal to 0. We get x equal to plus or minus 3. So I think with all this information, we can graph. There's a line here that I could use, I think, to just go straight. Good. Oh, I need the horizontal isotope as well. Horizontal isotope is the line y equal to 1. It's the x-axis, the y-axis. Remember, at the origin, we have a maximum. Oh, we get the vertical isotopes. I forgot those guys. We do dot, dot, dot with those as well. So it's plus or minus 3. It should be about the same. What is that? I won't erase it. Okay, well, not the same distance, but it's supposed to be. Anyway, I'm getting frustrated. So let's just graph the crappy thing, all right? All right. Now, you recall from algebra and connecting the calculus, look at 0, the graph is going up and then it goes down. So on the interval from -3 to 0, it's increasing, then it's going to drop, right? That looks horrible. I'm just going to instead of talking, it's about the same. Anyway, supposed to be smooth. From -3 to negative infinity to -3 is positive, right? It's increasing. The only place that it can increase is here, where it does this, and it's going up, increasing function. Right? From -3 to 0 is increasing. From 0 to 3, decreasing. And then from 3 to positive infinity is decreasing. But is it here? Now, if it's there, doing that is increasing. So it has to be here. So it's decreasing. Right? And they're all smooth. Okay. think that's it. We have a section later on where I can go into more depth, where I will connect the algebra and the calculus to graphing these functions. But for now, I think that'll do. Thank you.